All right, so I'm going to start off with just taking an example and working through it. So here is what people refer to commonly as a synchronous buck converter, right? You can recognize the buck converter structure with a single pole double throw switch followed by an LC filter. And how difficult can this be? You take the input voltage here, you switch these devices repeatedly at a switching frequency F sub S. You create a pulsating waveform at the switching node. The duty cycle of that pulsating waveform is the control variable that we refer to as D. And then you low-pass filter that pulsating waveform to generate an output DC voltage that is directly proportional to the control variable D and directly proportional to the DC value of the input voltage. So that's your buck converter in 30 seconds. The inputs in this case here would be the input voltage, the load current, and the control voltage that really sets the value of the duty cycle D. The outputs would be the output voltage, but also we treat the input current as a quote mark output, and you will see that has particularly importance in when we get to the point of designing an input filter. Then the responses from, for example, duty cycle to input current are going to be particularly important in studying how the input filter is going to respond to that type of perturbation. The state variables in the converter can be commonly associated with the energy storage elements. So here we have two energy storage elements in the low-pass filter, the inductor L and the capacitor C, and the voltage across the capacitor and the inductor current are the state variables in the converter. To make this a little bit more realistic, I'm including here some of the non-idealities in the converter. So we will say that these two switches have, when on, behave as on resistances. They're not necessarily the same. So we say R on 1 and R on 2 right here. We also take into account some series resistance for the inductor, and on the output filter capacitor, we take into account the fact that it's also not an ideal capacitor, but has some equivalent series resistance. Why is this called a synchronous buck converter? So normally in a buck converter, we have the main control switch and the rectifying diode right here, right? The diode would be pointing here. And you could just as well have a single controllable switch with a rectifying diode performing the function of the single pole double throw switch in the buck converter. That's perfectly fine. Instead of diode, we can employ an active switch, in particular a MOSFET, to have that switch conducting at a time when the diode would be conducting current. So when you turn off the main control FET, then normally the rectifying diode would be conducting automatically. You will have automatic commutation between the main control FET and the diode. But if in the process you actually turn on this MOSFET right here, you will have the current actually flowing through the channel of the MOSFET from source to drain. That's actually opposite of what normally the current would flow through a controllable MOSFET. And that MOSFET really serves the purpose that the rectifying diode would serve in just a regular transistor plus diode buck converter. Now, this MOSFET, the MOSFET, let's call it Q2 and Q1 are turned on and off in complementary manner. You will never have them both on at the same time, of course. And so this Q2 MOSFET has to be synchronized to the operation of the control MOSFET Q1, and in fact it has to be performing the rectification function in a synchronous manner, in a timed manner that corresponds to what the diode would be doing if the diode were present, which is why we have this term synchronous in the buck converter. Synchronous buck converter is a very, very common component. You probably have 10 of those in your pocket right now performing conversion from the battery down to various pieces of your smartphone. Okay? So it is a very, very commonly applied converter circuit. One little question, since we are discussing the review of the Intro to Power Electronics material, is why would we want to use here a synchronous rectifier, a MOSFET, instead of just a plain diode? Yes, so the point of using this MOSFET here is that the R-on resistance of the synchronous rectifier, R-on2, times the current that would be flowing through that synchronous rectifier from source to drain, would be less than the diode voltage drop, and so that implies reduced conduction losses. And that's particularly important in cases where you're trying to make this converter serve as a power supply with a very low output voltage. The example that we are going to do in just a moment is going to regulate the output voltage to 1.8 volts, right? If you were to use a diode that has a forward voltage drop of 0.8 volts, the efficiency of that converter would be horrendous because that diode drop would be comparable to the voltage you're trying to regulate. Instead, you employ a MOSFET that has a very, very small on resistance and has the forward voltage drop in conducting current much lower than the forward voltage drop of a diode. One last comment about the synchronous rectification right here is that whether you sketch this diode here explicitly or not, I'd like to remind you that this diode, in fact, does physically exist as a body diode of the rectifying MOSFET. Okay, so the MOSFET comes in with the PN junction diode between the source and drain terminals. We don't like that diode to conduct because it has a large forward voltage drop. Instead, we bypass that PN junction diode that's built into the MOSFET structure itself by turning on the MOSFET channel and conducting current through the channel of the MOSFET with a voltage drop much smaller than the forward voltage drop of what would be the drop across the body diode. Okay, all right. So this is the type of little bit of a review of the very, very beginning of the Intro to Power Electronics. You learn how converters work, how they switch, and some of the details related to conduction losses and so on. So if you need to go back and review some of that, some more, do that. What we will do for the most part in this class is look into the dynamic modeling and control aspects.